recon in Turkey, so I think this is a pretty new talk, and I'm pretty excited to have her talk about what she did over there. A little non-traditionally, I'm going to start, because if you know me, you know I like to talk. I'm going to give just the geology of the earthquake, so it's just a brief summary. I did this with some EarthScope slides, so that's what's here. These are online teachable moments from EarthScope. You can Google that and check these out as well. And I've just doctored them and put in a few things that I wanted to talk about. So I'm going to give the geology of these earthquakes. Anyone here want to say the name of the earthquake sequence? Kahramanmaras. Rolled off someone's tongue the other day. Okay, so this is the Turkish earthquake sequence that happened last February 2023. So this is, if you see USGS, did you feel it, or reports, you'll see often a beach ball diagram. So a lot of you have learned this in my course. Reported with other information like the local time, latitude, longitude, and depth. So those are usually the first bits of information we get after an earthquake. And so what we see from this beach ball diagram is that we have these dark areas, that's compression, and that's essentially the energy that radiated out away from that earthquake that happened, right, in the crust of the earth. And so these are first motions recorded by seismometers. We can plot them out in this way, and what we see is we have compression and tension in these white areas, compression in the dark. And so the solution for this pattern is two fault planes, one that would trend kind of northwesterly and one that would trend northeasterly. And so when we look at the kind of signal of aftershocks that happen in the area or felt reports, you'll notice that it fits nicely with the Eastern Anatolian fault zone here with the northwest trend. So the first earthquake was magnitude 7.8, the Pazyryk earthquake. It was about 17.9 kilometers deep, and it occurred here on the Eastern Anatolian fault zone. That's this lower star. This is the strongest earthquake in the region, more than 80 years. There were, I think at the time this was put together, hundreds of buildings, but I think it's actually in the tens of thousands, not millions, but Diane has seen it firsthand, so we'll hear more, that have collapsed or had structural damage and can't be re-inhabited, and more than 52,000 deaths, both in Turkey and Syria, and I think that number is actually greater than this. Really interesting to the earthquake community was that 9 hours later, there was a large magnitude 7.5 earthquake that occurred to the northeast, and that's shown by this star. Okay, and so this is the seismicity after the magnitude 7.8 earthquake. 7.8 earthquake is here, and so you can see seismicity occurring after that. And this was in the 9 hours just after that earthquake, just prior to the magnitude 7.5. The magnitude 7.5 earthquake occurred, and that's shown here. And we're starting to see aftershocks now in this other kind of east-westerly trend. And that was the Elbistan earthquake. So I pulled this from a recent paper. This was published about a month after the earthquake. The Arabian plate is converging with the Eurasian plate. And I want you to imagine that you have a P in between your fingers, so everyone can do that, right? So we have a P in between our fingers and we're squishing down, right? And we've got mass over here and we've got free space over there. And so that P is going to shoot out the side, right? And so the top of your finger would be the North Anatolian fault zone, and that lower finger essentially is Eastern Anatolian fault zone, right? And so that's what we're seeing here. There's our North Anatolian fault zone, East Anatolian fault zone, convergence between the Arabian plate, Eurasian plate, and the Anatolian plate is essentially extruding in this direction. Okay, I really like this figure because it shows us the number of aftershocks for both of these earthquakes in just 1 month after the main shocks, so the 7.8 and 7.5 earthquake. And so this is, you can see the decay and the number of aftershocks here, and that's through February 28th, from the 6th to 28th. So I just went over this again. Arabian plate is colliding with the Eurasian plate and extruding the Anatolian plate in this direction. Zooming in a little bit more now, we see the Eastern Anatolian fault zone isn't quite as simple as I described. So there's thrust faults in here and other faults, but the main shock, the 7.8 earthquake is here. 7.5, we're going to zoom into that blue box now. And so the 7.8 earthquake epicenter is shown here on the East Anatolian fault, and it ruptured to the northwest. And then again, 9 hours later, we had probably a stress change in here and a fault that was pretty far into its earthquake cycle. And so we had a magnitude 7.5 earthquake within just hours of that first main shock. And that's a quickie on the geology. And now I'm going to leave it to Diane. Thank you, Diane.
All right, thank you, Ashley. And yeah, thank you all for having me today. I'm excited to present about this. The earthquake, of course, happened last February. And so at this stage, the work that we put together is very much on our observations and a little bit of interpretation of that. But the next steps are to go back to Turkey within the coming months and collect some subsurface data to allow us to do further analysis to really understand what happened and what the earthquake hazard, what we can learn from it here in the US and the Pacific Northwest. So what I'm focusing on today are key geotechnical observations. Since I was part of the geotechnical team that went there, I do provide some observations of structural damage, but for the most part, it's the way that the soil has interacted with the structure to induce that damage. So as Ashley already presented, the earthquake event, we had the 9.8 main shock here, and then a 7.5 event 9 hours later that some folks are referring to as an aftershock, and then others as just another earthquake itself. So a huge and unprecedented event, these two earthquakes together. And then numerous aftershocks following these events up to a magnitude 6.7. These are the ground response following the two ruptures. This is the first event and the peak ground accelerations following it. And so from this, we can kind of map out the areas that we expected to see the most damage. Most of the concentration, of course, along the fault. And the areas that we focused on were Iskenderun down here, Golbashi, which is, I believe, up north. I can't make it out without it on the map. And then we also spent some time down in Antakya as well. And then the magnitude 7.5 event that happened later on. And you can see that there is some overlap in areas, particularly up here in Adiman, where these areas were shaken twice by these very significant events. A summary of the loss of life and damage that occurred from these events. Almost 60,000 deaths in Turkey and Syria that were attributed to the earthquakes. I pulled this figure off of Wikipedia, so it's not vetted, and I think that a lot of it relies on government reporting. So these numbers very well may be larger. There was widespread ground failure and liquefaction that impacted structures, bridges, lifelines, ports, and dams, and then many collapsed and heavily damaged buildings. From the report, which I referenced at the end, there were over 35,000 buildings that were collapsed or partially collapsed, and then almost 180,000 that had heavy damage that I think did require demolition. So our reconnaissance efforts were as part of the Geotechnical Extreme Events Reconnaissance Association, or GEAR for short. And then they mobilized in partnership with researchers at Middle Eastern Technical University out of Ankara, and with their Earthquake Engineering Research Institute. So this became a multidisciplinary reconnaissance effort with partnership between these three sources of researchers. And we were on the ground, the various teams were on the ground in the weeks and months following these earthquakes. The goal of the reconnaissance efforts were to collect perishable data that is going to disappear in the days and time following the earthquake. So things like ejecta, lateral spreading observations, even rupture observations that then get eroded and disappear in time. And then these are then developed later on as more data are collected and the results are processed to create valuable case studies that we can then learn from. The focus for us is on the impacts to infrastructure. And the advantage of going to Turkey is that the seismic code and the construction standards in Turkey are comparable to those in the US. So we can learn quite a bit from what performed well or did not perform well in Turkey. The team that I was a part of, we were on the ground from March 27th to April 1st. We were a small team, 4 of us, with researchers from University of California, Berkeley, Ohio State University, myself, and then Sena, who was our Turkish host, who did the most work out of any of us. You can see we were there fairly far after the earthquake, so we didn't get to see a lot of observations of ejecta or things that may disappear and erode over time, but we were still able to observe buildings and learn from previous researchers where the liquefaction had occurred and where we should go. The three areas that we spent our time at, we spent most of our time at Iskenderun, and then a day at Gulbashi up north, and on Turkyie down in the south. So that's where I'll be focusing most of my presentation on today. Objectives for this presentation. I want to highlight some of what I consider interesting or that are novel geotechnical earthquake observations. And then also summarize remaining questions from these earthquakes, areas that we plan to focus on to learn from these earthquakes, and that can then provide some lessons for us in the US Pacific Northwest. So starting with Iskenderun, and like I said, this is where I'll be spending a lot of my time in this presentation. What we saw in Iskenderun was that there was extensive liquefaction and lateral spreading within the city. There was a lot of building settlement and ground deformation due to this liquefaction, as well as frequent flooding that has followed these earthquakes. Some background on Iskenderun. It's located on the Mediterranean Sea or in the Bay of Iskenderun, as you can see on the last map. It's historically a port city. It's the second largest port in Turkey, so its functioning is pretty important. It's historic, like I said, and you can see with that we have access to historic maps and photos to really get a feel for how the city was developed and how it's been built up over the last century or so. So these are the same buildings in both pictures. On the left, I think that's from about 1916 or predates 1916. And you can see that this building, the old community center, sits on the shoreline, which has now been built out. One of the main boulevards runs along that historic shoreline. And the land has been built out further into the sea from there. It's located on an alluvial floodplain, largely developed within about the last century. And historically, it's been described as a swampy city, meaning that just poor drainage throughout this alluvial plain. And a lot of disease was attributable to this area within like the last century. And so it did take a lot of effort to develop it, and a lot of drainage infrastructure efforts or projects were undertaken. So this is one of those historic maps that we've learned from to understand the development of the city and how the shoreline's been built out. And with this aerial image here of Iskenderun today, the hatched area is just our interpretation based on these historic shorelines of where the land has been reclaimed and built out with fill. So you can see that there is a significant part of the city that is now located on this reclaimed land. And this is where we largely saw a lot of liquefaction occur. Another photo on the top here, this is an aerial photo from 1969. And this is from a recent publication as well that is really nice to picture the development since like 1915 or 1916, midway, and then today. So we can see on the top aerial photo that they published their outline of the current coastline. And so we can see that progress of the coastline over the 20th century. The subsurface conditions in Iskenderun, a lot of young quaternary alluvium from fluvial and coastal processes to about 40 meters deep. Iskenderun is in a basin, so we do expect basin effects from the earthquakes. Very loose to loose silty sands. We see on these three boreholes that are all located fairly close to the coastline, but not on any of that reclaimed land. We have SPT blow counts between about 2 and 12, so very loose soils, and for the most part, silty sands extending to about 30 meters depth. So we expect similar soils for the most part along the coastline. The seismicity in the area, there were several seismic stations located near Iskenderun. We have access to records from these three shown here, 3112, 3115, and 3116, with their shear wave velocity profiles shown on the right, just plotting the top 30 meters of shear wave velocity. And 3112, this is the station that's in Iskenderun, closest to the areas where we were able to building damage. And looking at the recordings from these ground motions, I'm only showing the magnitude 7.8 main shock. It's pretty apparent that this is what shook Iskenderun the strongest, where the earthquake was felt. The magnitude 7.5 aftershock or second event didn't wasn't really felt in Iskenderun. So most of the damage is attributed to the 7.8 event. The station in Iskenderun, 3112, unfortunately, it cut off early during that main event. You can see it stopped here. But we do have recordings at the other two stations, which are on stiff soil or soft bedrock. And this will take further analysis, but what we can see from an aftershock that was recorded by all three stations is that there are amplification effects at the station 3112, which would be expected to have occurred during the main shock as well. Based on ground motion models that they've been putting together with a team from UCLA, the expected peak ground acceleration in Iskenderun is about 0.3. So the soft soils in Iskenderun appear to have amplified the ground motions. All right, so now talking about what we saw on the ground in Iskenderun. Like I said, there was a lot of liquefaction and lateral spreading that coincided with the historic shoreline, which runs about along that, that blue line there. And also, of course, on the reclaimed land. I have observations of ejecta that were observed by some of the first reconnaissance teams, and then as well as areas where we took lateral spread measurements with those displacements plotted there. So this is approximately a map where we went and where we saw major liquefaction in the red area, and then some marginal or minor liquefaction back here. But this is a limited map just to where we were able to make observations. Some examples of evidence of liquefaction that we saw: lateral spreading and ejecta in the background, more ejecta and lateral spreading cutting across roads. These images are from the days following the earthquake, and I believe that they were taken by local residents, where you can see the amount of ejecta that was initially covering the streets in Iskenderun was quite significant with this ejecta all through here. So what we did when we were on the ground is we focused on buildings that had settled and looking at building settlement, so we can understand the role of liquefaction on building damage and building settlement. These are the groups that we surveyed, group of buildings that we surveyed in the northeast part of Iskenderun, in an area called the Chai district, which is entirely founded on reclaimed land. In total in Iskenderun, we surveyed 23 buildings, and there were settlements from 0 to 740 millimeters that we observed. So some buildings like these, which perform very well, these are buildings on pile foundations and high-rise buildings. Negligible settlement of these buildings. And then for the most part, these buildings, which were 5 to 6 story buildings, they saw significant liquefaction and settlement, or liquefaction-induced settlement of these buildings. Like I said, all the way up to 700 millimeters of settlement. This is an example of one of these buildings that we surveyed in Iskenderun with very significant settlement. Our reconnaissance consisted of, we did laser level hand measurements, so selecting a place that was assumed to have not settled or been displaced by the earthquake, far enough from the building not to have influence. You can see the laser level right here, and then measuring where that laser level falls on the building and measuring from the base of the building up to that laser point. It can be challenging, given that liquefaction was so extensive in this area, to select a point which was unaffected by liquefaction. And so these measurements do need to have some consideration and some understanding of the variability or uncertainty within them. But between various teams and various researchers in the field, we kind of do the best that we can to get these measurements. And then we also did LiDAR analysis using Adam's LiDAR device. And so at the edge of you can see, we shot LiDAR, I believe, from here and here at this building, and then fit to the data at an initial reference plane, assuming that there's a little bit of a gradient to the site, and then could look at the settlement of the ground relative to that initial reference plane and get a sense of things. The LiDAR turned out to be invaluable for just being able to analyze and reanalyze the ground deformations. And I'll show some of the observations that we were able to make using LiDAR that I don't think we would have been able to get without the LiDAR. So it turned out to be quite a valuable tool for us to have. This building was quite interesting. You see that there was significant liquefaction settlement at the building. And you can see this pattern of deformation and ground settlement around the building. And that's because the foundation of the building has a full basement and then a slab that extends 1.5 meters out around the building. And so you can see this interaction of the foundation with the ground settlement around it. That's picked up both here in the picture and then also in the LiDAR as well by this deformation. So we did see a lot of interaction between the buildings and the ground deformation. So I'm going to focus on 3 cases in Iskenderun of building ground interaction that we saw. I'm going to start with this case up here. We call it the kindergarten case because this building here is the Iskenderun kindergarten, located along the historic shoreline, so not on fill. Then I'll move down to this group of 4 buildings. These are residential commercial buildings, and then the Palette Hookah group, which this restaurant in the middle is called Palette Hookah. So I'll be focusing on these 3 and kind of building our observations from these 3 groups of buildings. Starting with the kindergarten, this is the kindergarten in the background. So we're on the historic shoreline facing inland. And what you can see at the kindergarten, in which it was apparent on the ground and also in these pictures, is that there's a mounding of the ground. It's kind of curved downwards. The kindergarten itself did not appear affected by the earthquake or by liquefaction. It performed very well. We didn't see evidence of liquefaction around the kindergarten or any settlement at the kindergarten. But the buildings on either side, we measured this building on the left, 5-story mid-rise building, 420 millimeters of settlement. And then this building on the right, or the west, 450 millimeters of settlement. So significant settlement took place on either side of the kindergarten. And yeah, you can see that the ground deforms. There's about 9 meters in between those 2 buildings where it appeared that the ground was not affected, and then back down to that deformation. And what we think happened here is that each of these buildings settled and started to drag the ground down during their settlement. They didn't have basements. We talked with folks on site there and building managers. There weren't basements, so there were just shallow foundations. And as the building settled that significant amount, they just dragged and affected that ground around the building. And now when there's 2 buildings on either side, it looks like the ground is mounding like this, and we call it a hogging deformation, like a bending convex down of the ground. And so now when we move over to this group of 4 buildings over here, I'm standing here, actually this is the LiDAR in the middle of the courtyard of these 4 buildings, and you can see that mounding happening between these 4 buildings. So this one is facing to the west, and then we move around, and we're facing to the east. The 2 buildings here, these were very similar buildings, similar construction, similar design, and from Google Earth built at the same time, and the same story with these 2 buildings. And they actually performed remarkably similar in the earthquakes as far as settlement goes. We shot LiDAR in this courtyard. And from that, again, looking at an initial reference plane, we could see that there's this mounding of settlement happening and dragging down from the buildings on either side, causing the curvature of the ground. And the LiDAR was really valuable for being able to observe this. Let's see it. In these pictures here, we're facing to the north towards the water, and then here we're facing towards the south. And as I mentioned, the buildings that appeared similar design construction, they performed very similarly, had similar scales of settlement. This building and this building settled similar amounts. This building and this building settled similar amounts. And whereas at the kindergarten, where it appeared that the buildings had settled on either side and were dragging down the ground, but there was 9 meters in between that was unaffected. What appeared at this site, based on the LiDAR actually, is that the buildings were close enough together that dragging down, there was interaction between it, and in the middle of them, there was settlement. So just based on the LiDAR, we could look at those subtle differences in the ground and see that there was areas on the sides of the buildings that hadn't settled, but then at the middle of that mound, there was also a dip down. So this is the mechanism that we believe is happening at this group of 4 buildings. Now moving on to Palette Hookah, just a few buildings away. This is Palahuka, a small steel frame restaurant, lightweight, single story, between two larger mid-rise buildings on either side. And from surveying a point on the sidewalk here, this building to the east of Palahuka at this corner settled about 400 millimeters. This building settled 510 millimeters. Whereas looking at Palahuka, it didn't look like it had settled much at all. For measurements in the middle, it was about 20 millimeters. But you can see that there's this obvious curving of the building, that the building itself has now fallen onto this curving of the ground. And I have some more photos here to get a sense of what's happened. And we can see that there's curving of the sidewalk in front of Palahuka. There's tension cracks in the sign and the retaining wall out front, consistent with that bending. And then looking at the concrete slab, the floor of the building, you see tension cracks running parallel from front to back. So I'll just highlight them here. Oops. There we go. So those cracks that are running there. And so what it looks like happened at Palahuka was that this building that was otherwise unaffected by liquefaction was damaged by those two buildings on either side of it, dragging the ground down and that hogging ground deformation. And this hogging ground deformation is something that we hadn't observed, or I should say, when I say we, I mean the rural, we geotechnical engineers looking at earthquakes, hadn't observed before. We've seen this happen over a building itself as the building settles and the foundation deforms and hogs, but to have buildings settle and induce this in the ground around the buildings, we hadn't observed before. And then seeing the implications for a building adjacent to another, that there's these interactions potentially between buildings that we need to account for, and seeing damage at an adjacent building, we think that there's a lot that we can learn from this. All right, okay, so now moving on from our building observations, something else that we saw in Iskenderun that was quite surprising to us is that the day that we were there, March 29th, and actually, I don't know if anyone noticed in that picture of the four buildings, there was floodwater around the base of the buildings. That day, March 29th, there was significant flooding that took place in Iskenderun. Talking from a local resident there, they said that there was flooding every few years prior to the earthquakes. But then since the earthquakes, that flooding is happening every couple of weeks when there's high tides, rain, wind. And we saw it when we were on the ground, like folks were pumping out their basements in the Chai district. And then we actually saw the flooding happen on March 29th. So it seems that now this is something that folks are living with in Iskenderun, is this regular flooding. My colleague Patrick, who was on the ground with me, he put together this map showing the extent where we observed flooding on March 29th, which is this blue line here. So just a little bit inshore from the historic shoreline. And then some pictures of the flooding that we saw. So let's see. This building here is the first one that I showed. So flooding past those buildings into the next street in. This is the community center and the historic shoreline here. So flooding about 2 blocks into the city is what we observed on March 29th. And we think it's related to the bigger story of what happened in Iskenderun. But this underpass, which runs through the south part of Iskenderun, this is from Google Earth in the days following the earthquake. We did see flooding in this underpass. And so it looks like the soils in Iskenderun are just loose, subject to liquefaction and flooding in this case, relieving the poor water pressures into this underpass. And actually, historic accounts of earthquakes that have shaken the region, when they call out Iskenderun, they note that there was in Iskenderun from these historic earthquakes that there have been times when the water table rose up above the cultivated land and flooded the area. So this seems consistent with past patterns of earthquake damage. So what Patrick has done following the earthquake and our observations of flooding is he's collaborated with folks to look at INSAR data, to look at subsidence rates in the region, or subsidence rates in the region. So this satellite data, looking at subsidence for about 3 years prior to the earthquake, or 2 years, And the rates of subsidence are about 5 to 6 centimeters per year. And then granted, this is only in the few months following the earthquake, but they see subsidence rates of 20 to 30 centimeters per year. There's possible seasonal effects from this. We need to continue to monitor and see what's happening. But it does appear what we're thinking happened is that the area may have been subsiding a bit, but the earthquake appears to have caused this accelerated subsidence, and widespread regional liquefaction has lowered the elevation of the ground, just making everything or the city itself much more susceptible to flooding. And so we are observing this kind of co-seismic hazard of an increased flood hazard in the area due to the earthquake. Okay, those are the main observations from Iskenderun. Now moving on to Gulbashi, up here in the north. This area, it was significantly shaken. You can see, actually that might just be a splay of one of the faults, but you can see that it's very, very close to the main fault, the Eastern Anatolian fault that ruptured, and then it was strongly shaken by both events. What we saw in Gulbashi and other reconnaissance teams is extensive liquefaction and lateral spreading, particularly in fine-grained soils that have plasticity from 8 to 14. So whereas in Iskenderun, we saw kind of classic liquefaction of sandy soils, in Gulbashi, we're seeing some of those not so well known or documented cases of plastic fine-grained soils. And there was severe liquefaction-induced building settlement throughout Gulbashi. The setting of Gulbashi it's a lakeside city at about 866 meters above sea level in a mountainous area, bordered by the Eastern Anatolian fault zone and severely shaken by both of those main earthquake events. Unfortunately, there is a seismic station in Gulbashi, but there weren't any usable recordings following the earthquake. And the nearest seismic station is about 40 kilometers from Gulbashi. So there's going to have to be some ground motion modeling done in order to understand the seismic demand in Gulbashi. Yeah, so here's Gulbashi, and that's the station that didn't work. And then here's the strong motion station surrounding it. Our team just looked at a very a constrained part of Gulbashi here, but we surveyed building settlements and tilts throughout Gulbashi, and I think that there was about 13 buildings that we looked at. So here's an example. Here's just looking down a street in Gulbashi. You can see, in some sense, the range of performance that occurred in Gulbashi. This building, I believe the settlements at it were like a meter, like really significant settlements that occurred at some of these buildings. Significant tilts at many buildings, and then some which you can't quite make out down here, but that performed actually fairly well, just relatively minor amounts of settlement that were observed. There was also, while we were there, still ejecta that was on the ground, and I think we have to think that it wasn't eroded away by weather because it was that plastic soil, right? That plasticity that isn't as susceptible to erosion. So this is an example of some of the ejecta that we saw, and you can see the distinct color of the soil, that reddy brown color. This is an example of two buildings that were adjacent to each other. This is a single-story building, residential, actually 2 stories, sorry. 2-story building, performed very well. We didn't observe any kind of settlement at it, and there wasn't any apparent damage at this building. Adjacent to it, a different 2-story building. So from that sense, similar buildings, but with very different construction. Lightweight, wood frame, more concrete, reinforced concrete, heavier structure. And you can see just how much more settlement you had with this building. Almost a meter of settlement as it punched into the ground. And then actually, right next to this building right here, this is the building that also performed very poorly. And you can see that there's about a meter of settlement from the foundation failure at this building. Shoot. I'm gonna have to jump around for a second here just so I can situate ourselves. Next, I want to look at these 2 apartment buildings. This one here to the south performed very well, 10 centimeters or 100 millimeters of settlement. And actually, we think that it's between 0 and 100 millimeters average settlement, depending on how we interpret things. And then this building to the north, significant settlement, 240 millimeters. And what we saw was that folks were still able to live in this apartment building, but had moved out of this apartment building. And when we look at it, the difference was the foundation conditions. So both in the same soil, same seismic demand, same building, same construction, same ages, but one had a basement, which generally buildings perform better as far as geotechnical earthquake response goes when they have a basement versus buildings that don't. And so we saw negligible settlement on the north side, about 200 millimeters on the south side, but this is based on LiDAR analysis of these settlements, and it seems like that settlement may have just happened, consolidation settlement over time. It couldn't immediately be attributed to liquefaction or earthquake-induced foundation failure. But that tilt does seem to exist, so we do have to note it. And it's also consistent with pooling flood water that we saw in the basement on this side of the structure. That building to the north, which in this case had no basement and had significant settlement at it, which again, the LiDAR just helps us with this interpretation of the settlements, particularly with these large structures that we can't quite tie a survey to a single datum. And then this was not our team that made these observations, but I think that it is worth showing. This was a different gear team who went around the lake and looked at lateral spreading. And there was significant lateral spreading in this part here. You can see this is the Google Earth image before the earthquake and then after the earthquake, that lateral spreading and settlement of the ground. So this building is fully immersed. I think this building, they measured about 50 millimeters of settlement and overall about 2 meters of lateral spread at this site. And this picture here shows the folks on the ground surveying with drone footage, and it just puts into perspective just the scale of this lateral spread. Okay, now moving down to Antakya. This is an area that was really, really strongly shaken. There was very, very severe damage in Antakya. In some areas, over 70% of the buildings collapsed from the earthquake event. There was liquefaction that was observed near Antakya, but not in Antakya itself. And so what our focus was, for the most part, was a survey of bridges. And this bridge that we looked at was just north of Antakya, and it was closed due to damage from the earthquake. But to me, as an engineer, it hit home. This was a significant bridge for the earthquake response. You can see here is a stadium of the nearby bridge, and that it turned into a staging area for displaced families and people following the earthquake. You can see the tents that are in the parking lot there. And with this bridge closed, it didn't cut off Antakya, but it did make the route around to get to the stadium and back into Antakya significantly longer. And so there were folks that were taking this alternate route, but then there were also folks that were just bypassing the barricades to go over the bridge. And so some observations of what we saw, for the most part, this is a summary of our survey, but for the most part, it was structural damage. Components like this, which you can see that the vents during the shaking shook strongly enough to just damage some of those structural components. One of the vents here with damage installing. So for the most part, it was just strong shaking that structurally compromised the structure. But we did see some ground failures around here and slope failures. See the leaning transmission tower in the background. So there may have been some contribution of ground failure and soil interaction as well at this bridge. Yeah, we saw, I mean, just in surveying the structure, measuring the drop between the abutments and the bridge, and yeah. So, and then moving now into Iskenderun itself, this is a bridge, or I'm sorry, in Antakya, in central Antakya. This image, I believe I took it from Google Earth just a few days ago, but I think it dates back to May. But you can see just the level of destruction that took place in Antakya, where all these empty lots were once buildings. And so with this bridge, we surveyed it, and what was significant at this bridge was a retaining wall failure from that seismic demand. You can see on either side the failure of those retaining walls. And you can see that potentially there was movement of the abutments in to compress the bridge. You can see bending. Now that I've told you, you'll see it. You can see that bending of the bridge deck a little bit, and this utility line here you can see that it's loaded in compression, and there's almost like a compression S curve of that utility. So it looks like there was retaining wall failure, and overall the abutments of the bridge were compressing it. Also, significant displacement of the abutments relative to the bridge deck, limiting, of course, transportation of emergency responders, emergency response people following the earthquake, until something like this, a temporary solution, can be put into place. And then south of Antakya, this we actually didn't go see since it's fairly close to the Syria border, but I thought I'd include it because from a geotechnical perspective, it's quite interesting. Contacting in Canada, Tyler Southam, who was part of the Canadian reconnaissance team, he emailed these to me and asked if we saw them. No, it's too close to the Syria border, but thank you for sending. At this bridge, they observed ejecta and sand boils and significant lateral spreading from that liquefaction that occurred at the bridge. And you can see, as he pointed out, you can see that the pile of the bridge, you can see the torsion and the tilting of that pile that's then compromised the structural components of the bridge, likely associated with this liquefaction. And now looking head on at the bridge, you can see the damage and the associated damage at this bridge. But interestingly, it is a twin bridge. So this one did perform well. This remained open, whereas this part of the bridge still remains closed. So an interesting case here to then go back and understand what were the differences between these bridges. Why did one perform well while the other was damaged severely by liquefaction? And then the last one that I'll point out here, this is a hospital in Antakya. That new hospital was built, I think, looking at Google Earth, I think construction happened throughout 2016, but the hospital remained fully closed following the earthquake. And I don't know why it was closed, whether they were concerned about structural integrity of the building. They did staging and had a lot of emergency response staging in the parking lot. But what we did notice as we walked around this hospital were a lot of cases where the fill had settled, and especially at the entrances, like ramps, loading docks here for the emergency room, you get this fill settlement limiting the response to go into and out of the hospital. Like you can't pull up ambulances now to this entrance or move wheelchairs or dollies in and out because there's this kind of damage that now has to be overcome. And then this is settlement around utility lines here. So to me, when we think about fill, at least as geotechnical engineers, it's simple, right? Like we learn about it in our introductory course, how to do compaction and fill, but it matters. It matters that we do it right, that we don't overlook anything, and that those spaces that are maybe difficult to get to compact, like next to a building, that it matters, and that we make sure that that fill is compacted correctly. So I just wanted to include this here. All right, so it's a summary of the reconnaissance. What we're continuing to look at, we're planning to go to collect subsurface data. So now we have those observations of building performances. We can use the data at hand to understand the seismic demand, but we also need the subsurface data at all of these locations. So we can tie those three parts together to really develop nice case histories and learn from them. I said seismic modeling to understand the seismic demand in Iskenderun and Gulbashi, and then also looking further into this influence abilities on the adjacent grounds and adjacent buildings. Why did this type of interaction occur? What kind of conditions make the ground susceptible to this kind of interaction? I also think we need to start, I shouldn't say we need to start. I think this is another lesson that we need to account for long-term co-seismic hazards, such as flood hazards, to understand just what may be, what those long-term consequences of an earthquake may be in a region. And look into what areas are susceptible to these kind of co-seismic flood hazards. And then also, of course, in Gulbashi, those fine grain and plastic soils, those are quite interesting and will make really valuable case histories, particularly when we think about the Pacific Northwest. So thinking about what we saw there and how it can be applied here to the Pacific Northwest, my mind always goes to the critical energy infrastructure hub along the Willamette River. We saw lots of liquefaction, building settlement on reclaimed land in Iskenderun. That's the CEI hub right there. So just driving home, learning from that and understanding further, I guess, that reclaimed land liquefies. Fine grain and plastic soils, we have lots of these in the Pacific Northwest. We need to consider them an earthquake hazards, and we can learn from them and apply those lessons here. Aging infrastructure constructed before our awareness of seismic hazard, like the CEI hub. Pro-seismic hazards such as flooding and landslides, and then of course thinking of the emergency response here impeded by liquefaction, ejecta, blocking response routes that covers the roads, bridge abutment settlement, and then also settlement outside of hospitals, fire stations, and other areas that limit our emergency response. So, I want to include this slide of how to get involved if you're interested in reconnaissance as a student. The Earthquake Engineering Research Institute is a great pathway into this. It has engineering in the name. There are lots of engineers in it, but there's also lots of geologists and seismologists within EERI. There's a student leadership council for graduate students. You can talk to Kayla for more information if you're interested. They have annual meetings, lots of support for students, seismic design competitions for undergraduate students. You can support reconnaissance virtually by being part of a virtual reconnaissance team to take data from Twitter or news stories to then help teams on the ground. And they also often do reconnaissance trainings in partnership with organizations like GEAR. And then of course, earthquake hazard research projects at PSU. Great way to get involved. This acknowledgements, Adam, your top tier for letting us use your LiDAR. We really appreciate your trust in letting us do that. And then of course, the team that was on the ground with us in EER and NSF. These are our reconnaissance reports. If you want to get a little bit more information and see, there's lots of information in them about what we saw on the ground and the other team saw on the ground. And I think that that's it. And so happy to take any questions.